different parts. The first part here only depends on the number operator, and it becomes a diagonal matrix. But those operators here are not diagonal matrix, and they depend on the number of bosons in the system, in this case in a diamond. We use this basis in order to, well, we will apply those operators to this basis and obtain the eigenvalues. We will diagonalize the matrix and obtain the eigenvalues and eigenvectors. So we can take the first case. The first case, we put two bosons in a diamond. We have three different states. The first state here means that we have two bosons on just one side and 0 bosons in the other side. This here means that we have 1 bosons in each side. So what we do, we just fix some of the Q parameters, and Q2 here is variable. So we plot the eigenvalues, and to do that we have designed a mathematical routine, and we plot 3 different eigenvalues here. This picture here shows the standard Bose-Hubbard model. All the pictures here are interesting, but we're interested on this picture. Why? Because we want to study those intersections. And we obtain those intersections when we put Q4 equal to 0.5 and we let Q5 be variable. So I will study those intersections later. We increase the number of bosons in the system to 4. Now we have 5 different states. We plot again the eigenvalues. We can recognize some of the behaviors. And again, for the same configuration of Q parameters, we obtain the intersections. In the previous one, we had 2 bosons and 2 intersections for these configurations. And now we have 4 bosons and 4 intersections. Can be interesting. So now we study this point. This is one intersection. Yeah.